That'd be a good time capsule to get in and go back and see some of these guys in their outfits.
And then you get back home real quick.
Yeah, right. Don't get trapped in Victorian
don't get
England. No penicillin yet. Yeah. Okay, so we've covered a lot so far. Like I said, Chapter 4 is a pretty big one. We've looked at Newton's laws, looked at units versus dimensions, looked at force, mass, acceleration. We've defined energy and power in terms of force, distance, and force and velocity. Talked about the fact that energy and work are the same thing, have the same dimensions, the same units, interpret a little bit differently, and that energy is sort of all around us, but work is what we do. Push in your chair, drive your car, move things around, pump water up a hill, spin a turbine, etc. We did a neat little problem with a wind turbine with air moving through it. We defined kinetic energy as 1/2 mv squared. We also went back to our equation of power being energy divided by time. Defined the watt as 1 kilogram times 1 meter squared per second cubed, and derived that, these big turbines, run about, 1.5 megawatts. That's enough to power, at least 1,000 homes. The electrical demand for a house is about a kilowatt on average. So there you go, about 1,000, maybe 1,300 homes. We also defined a new type of energy called potential energy. We tied that in with the Gordon Butte Dam, or Gordon Butte pumped hydro, as a way to store up piles of water instead of piles of coal. We went through Joule's little experiment. We talked about torque. As it turns out, I'll just let you in on a little secret. Energy and work and torque. Kind of weird to think about. Torque has dimensions of foot-pounds, distance times force, also Newton meters, distance times force. So torque also has the same dimensions as energy and work. Kind of weird, but true. We did Joule's little experiment where the harder you push with torque, the faster it goes, angular velocity, and the longer you spin, you can then change the temperature. Change it high enough, it starts boiling.
Is torque strictly a mechanical property?
Torque is strictly a mechanical property.
And spinning?
Yeah, I mean, you could think of it, if you get down to the quantum level, I don't.
I guess the angular velocity is more of the spinning factor, right?
Angular velocity is just how fast it's spinning, exactly.
Okay,
If you want to, torque is how hard you're pushing.
Okay,
Yeah.
and it could be in any direction, like linear or...
Well, as it turns out, torque, like force, is a vector. And I'll show you why really quick. So I can take this pen and spin it about this axis. I can spin it about this axis, or I can spin it about this axis. So you can actually torque things about 3 separate axes in the same.
Like X, Y, Z.
Exactly, Y, Z, exactly. In the same way I can push something up or down, back and forth, right and left. So force and torque are actually vectors. We're not going to get into it in this class. Most of the numbers we deal with are scalars. They don't have a direction. Like temperature is a scalar, it doesn't have a direction. Mass is a scalar, it doesn't have a direction. Yeah.
Final equation, you've got 3 T's. The first one's torque.
I know. Yeah.
And the last one's time. What's the middle one?
Yeah. This is torque. This is time. Little t is time, and big T is temperature.
Oh,
I'll typically use the big T for temperature, little t for time.
Okay.
Yeah, that's a really good point. Really good point, Tyler. Thanks for bringing that up. And then the tau is torque. Yeah. Alphabet soup. And the delta just means change.
And that already refers to thermal.
That refers to thermal. Yeah. Yeah. And I think what this also should bring home the fact that heat and temperature are 2 separate things. Heat is measured in joules because it's energy. Temperature is measured in Kelvin or Fahrenheit. It's just temperature. So Heat and temperature, two very, well, I don't say two very different things, but
But you can measure in temperature.
you can't measure heat and temperature. If you know the change in temperature, and you know how much of it you have, and you know the specific heat capacity, then you can measure the heat,
Oh, for what you're changing the temperature.
what you're changing the temperature of. And it's funny, I had this conversation, there's a geoscientist on main campus who, we were standing there in the Browning, lobby of the Browning Holiday Inn. He put his hand on the stone in the lobby and said, you can tell if this is fake stone or real or artificial because of how hot it is. Well, the stone in the lobby is the same temperature as the air. It's the same temperature, unless there's like geothermal flowing through it or something like that. But every object in this room is roughly the same temperature. We're not. We keep our bodies at 90. But everything else, the walls and the air, they're the same temperature. What's different between the two types of stone is the heat transfer coefficient. It's the same thing. Stick your arm out into 32-degree air versus 32-degree water. You'll know the difference. It's how quickly those materials transfer heat. Same thing with your different type of jacket, a cotton jacket versus a wool jacket. They just transfer heat at different rates. Yeah.
So you're saying when you touch the stone, you would like absorb its heat and you'd tell the change in temperature?
Yeah, and he said, oh, this is colder. Like, no, it's not colder. It just feels colder because it's sucking heat out of your body faster.
Yeah.
Yeah. So, temperature and heat are not the same thing. Heat is measured in joules, temperature is measured in
Being a
joules.
geologist, like I always look down at rocks and everything.
Yeah.
My daughter now will find a cool rock and lick it to see all the laminations and
Yeah, yeah.
the grains and everything better.
A lot of senses there.
So I was like, nice, my little scientist. Keep away from the social worker side.
Yeah.
Come to the dark side, daughter.
Okay, we're on figure 7, and I want to get through about 5 more here. So the next thing I want to show you is electrical power. And electrical power is just this: P equals I V. Now that's not volume, that's not velocity, that's voltage. So, sorry, we kind of ran out of letters, but that's voltage. So this is current times voltage. And if I just go to a electrical outlet, we know that the voltage is typically, let's just say 110 volts. If my fridge is running at, let's just say 7 amps, power equals 7 amps times 110 volts equals 770. And here's the really fun, cool thing about it: watts. 1 amp, and there was a French. We're out of England now. We're into France. There was a French scientist named Ampere. That's what the amp is named after. And then it's not Voltaire, but Volta, I think was his last name. So the volt was also named after a French scientist. But you multiply an amp by a volt, and you get a watt. And there was a British scientist named James Watt who will meet shortly, and that's the unit of power was named after him. So pretty cool that we can do exchange now between mechanical power and electrical power. Because then, right here, there's my heating coil. And if I measure the amps and I know the volts, that's how many watts are flowing in, and now I can see how much hotter, how many joules went into my system. And then to get the joules, pretty simple. The energy just equals the power times the time. So let's just say it runs for 60 seconds. So we've got 7 amps times 110 volts times 1 minute. So let's run it for 60 seconds. 770 times 60 equals 46,200. So let's just say 46.2 kilojoules. And you could take and convert that to BTUs or calories or kilowatt hours or whatever, however you like.
So the original number that you calculated would be joules, and then you can round it to be.
Yeah, that's exactly what I did. So I went in here and I said, oh, I've got 46,200 joules.
Gotcha.
I just took that decimal point over 3 places and said that's 46.2 kilojoules. Yeah, please. We'll open it up in 7 minutes. Yeah. Okay. So now, so we've come a long way. We've gone through mechanical, we've done thermal, and now we've done electrical, and we've tied them all together with the joule and the watt. Very cool. This is why this chapter is just so fundamentally important in this course.
You got a lot of like equations.
It's a lot of equations, yeah, and this, like I said, this is my favorite chapter for this very reason. I love these things. Well, it's the bread and butter of the engineer. You know, it's the engineer's job to broker among these different units. Okay, so there's joule. What's that?
I thought it was bacon.
No, there's Joule, Mr. Energy himself. Okay, so now this is kind of what's going on in, inside a solar panel, inside a copper wire. These are atoms. They could be copper atoms, they could be silicon atoms, they could be phosphorus atoms. You take a look at the periodic table, and let's just go back to the periodic table really quick. Dynamic periodic table. You kind of dig through this thing. My favorite thing to look at are the orbitals. As you click through here, you can just see all these little balls flying around. Those are the different electron orbitals outside of each of these atoms.
Oh, that's cool.
Yeah, it's really cool. You go to hydrogen, kind of boring, just a sphere. Helium, you got an up electron and a down electron. You pop over to boron. All of a sudden now you've got this sort of dumbbell-shaped electron flying back around and forth. So that's one model. Here's another model. Each of those balls is an atom. The positive protons in the center are attracting the negative electrons. But if you get them all in one place, they're sharing the electrons, if you will. So the metals, here are the metals down here. They sort of form this sort of hyper atom or large atom where the electrons are just flying back and forth. Copper, where'd you go? That's its shell. That very outer 4s electron you can see is very loosely tied. That 4s electron, there it is, right there. It's just sort of partying, all flying back and forth through electrical wires.
Just freely moving.
Just freely. You push it, you give it some voltage on one end, and they move. They physically move, not at the speed of light, but they move. The wave, the electrical wave, does travel at the speed of light. That's how we can talk back and forth across the optic fibers that are laid under the Atlantic Ocean, et cetera. But there you go. There's electrons flying through the.
Did you just say that there are fiber optic cables under the ocean
Oh yeah.
to transfer our phone signals?
Oh yeah.
Are you
Big time.
serious?
Oh
I thought
yeah.
it was all satellites.
Oh no. Yeah.
We're electrifying
A
the
ship
ocean
with like a
like
giant, cable, took it out.
Yeah.
Oh
Start
my
off as
God.
copper.
Yeah. It used to be copper. Yeah. Used to be copper. Yeah. Used to be copper wires for information transfer.
Well, plus, because,
No, it's
that salt water's not gonna do anything to copper too, right?
Well, it will. I mean, it's all insulated. But yeah.
Most of that copper came from you.
Yeah.
Oh,
Yeah. Yeah. It's true. It's true. Okay. Another important thing to know: V voltage equals IR. So there's your resistance. And you go back here to the periodic table. Somewhere down in here is tungsten. Tungsten is what's used in conventional light bulbs. You send electrons through it, it glows. Copper, obviously. So all these are, there's iron. It's a conductor as well. Aluminum's in here somewhere. And again, this is current. So here's another neat little trick. If I want to know electrical power, like how much juice is flowing through that wire in the morning to make my toast, we already know that P equals, IV. So now P equals I, and now what's V equal? Well, V just equals IR, equals I squared R. So the amount of power flowing through a wire is the current squared times the resistance. So in the case of your toaster oven, if you want it hotter, get some more amperage on it. And don't use a superconductor because it will never get hot. Use something with a high resistance, or a high enough resistance that it glows and makes your toast. Okay. There you go. Everyone's seen that. There's your battery. Chemicals. Now, this is chemical energy. And again, all of these atoms have, if we go to properties, somewhere in here is the electronegativity of each element in the periodic table. This is how much each of those elements likes having electrons near it. Fluorine, big time. Somewhere lithium has its own electronegativiity. So you can kind of like go through these different electronegativities. Lead, where's PB? So lead acid batteries. There's cadmium also used in batteries. There's lead. So when you have elements of different electronegativities, they're going to want to pull electrons towards them. When they pull electrons towards them, they flow.
So would
There you
they
go.
flow at different rates depending on the material?
Yep, they'll flow at different rates, and when all the electrons have flowed from from one element to the other, your battery's dead.
Oh.
Yeah, that's it. Yeah.
So electronegativity increases energy flow or energy?
Yeah, electronegativity,
So it's less
it's
resistant?
the amount of force at which it will flow.
Okay.
Right, and then depending on the resistance, it's going to flow at a different rate. And we'll grab it.
Depending on the element you're using?
Depending on the element you're using, yeah, exactly.
How long has that website existed?
Which one?
The P table?
I found that dynamic periodic table about 10 years ago.
Oh my God.
It
That would have been helpful.
It gets better all the time. I remember finding this thing, and one really fun thing to play with too is the temperature. You can take this thing and like
Oh, that's awesome.
just melt these guys.
Serious?
Yeah.
Sometimes that's the trickiest part of chemistry, just finding the information.
Yeah.
Everything.
I love this thing. I remember finding it years ago. I'm like, oh yeah, there it is.
That would have been so handy.
That's cool. That's a good one.
Yeah, no, it's a really good one. It's a really good one.
Serious.
Okay, well, I will see you all on Thursday. That was fun. Thanks.
Good luck.
Yeah, thanks.
I will be out of town.